even today, although we're in the age of computers and in the age of models and everything else, the reality is that most important decisions still are largely based on experience, limited data, and ad hoc approaches. And what we propose, and what many systems analysts and this whole area basically proposes, is that if we are to effectively address some of our critical challenges of our time, we must employ the use of systems analysis, basically quantitative modeling, simulation analysis, and computer-based decision support systems. Computers are not going to make the decisions for us, but they will support our decision making. That's the key thing I want to make. So it's not that we type our problem in the computer and it spits out a solution and tells us what to do. Certainly that's not the case. But what we do need to do is careful analysis, systematic analysis that can inform the final decisions that are eventually taken by humans and by experts. Okay? So by ad hoc approaches, for instance, people, let's say you're trying to decide between, what's the best hydropower plant to build. In some cases, some people may do a least cost analysis, what's the cheapest plant to build, and they'll do that. In many cases, there might be another situation where they just give it to the best contractor who has provided, maybe some incentives for picking that project, or a variety of other things. There is no traceability for how the decision was made, and there's no replicability, and there's no basis for why the decision was made for a particular case. So that's what I mean by an ad hoc. There's no system, a traceable system of arriving at a decision. And in most cases, what you find is, I work a lot in the sector in other countries as well, especially where there's more transparency. People are very concerned about making sure that there's a traceable decision, and there's a traceable trail where people can point, this is how the decision was arrived at, this was the logic that was followed. In most cases, it's not done in practice. Okay, so what about modeling? So I said, it's important we make models of systems and we analyze those systems and then make our decisions. So what do we mean by a model? I just want to make sure we all are talking about the same thing because we come from different backgrounds. An architect probably deals with, a small replica of a building that he may be making, or there are, physical models, prototypes in mechanical engineering, to make prototypes of products and so forth. But the kind of models I'm talking about are basically mathematical descriptions of real systems. Okay, these mathematical descriptions make simplifying assumptions of the behavior of a system. And they are used to predict essentially how a system would respond given a set of inputs. Okay, so model is not perfect. It's not a perfect representation of reality. In fact, that's one of the biggest challenges of models, that they do not represent actual reality. But if you have a good model, it will capture all the key characteristics of reality, such that it is able to predict system behavior given certain inputs. Okay, so modeling is not just a science; it's very much also an art. But at the end of the day, if you have a good model, it's a very powerful tool for systems analysis. So there are different types of models. Empirical models, in which you essentially use data to determine how two variables may be related. So you have a bunch of inputs, a bunch of outputs, and you can use statistics and many other techniques to figure out how are these quantities interrelated. These are called empirical models. Yes, absolutely, absolutely. So these are the inherent limitations of some of these approaches. But the argument is that this is one way of us trying to understand and predict reality better versus doing it all in our heads. So this is still a better approach in which we try to make the best decision available given the data that we have. But of course, the data may not always be perfect, and it never is. In fact, it's almost never perfect and it's never complete. So that's right. That's right. So you basically, your mental models are made explicit here, which is important because that allows for important conversations, and it allows us to correct some of our assumptions, perhaps, when we share it with others. Exactly. So this makes our mental models explicit. Okay. So there are other types of models as well. Physics-based models, in which you basically use governing equations of physical processes and natural phenomena to predict system behavior and system response. Okay, and we saw some hydrological models yesterday and so forth. I think most of you are probably aware of these types of approaches. So just to illustrate that there are different types of models that can be employed, and once you have developed these models, you can use the process of simulation, in which you exercise the model to predict system behavior under a given set of explicit conditions. Okay, so in systems analysis, there are a number of different types of methodologies that have been developed pretty much over the last 50, 60 years or so that collectively are, that collectively fall under this umbrella of systems analysis. I've listed out a few. This is no means an exhaustive list, but these are very common ones that you will encounter or may encounter or may already use in your professional work. So there's a whole body of work and a whole lot of set of methods called that fall under the umbrella of decision analysis. A lot of this work was done again in the 20th century. Kiwi, Howard, Dreyfus, there were some of the pioneers at Harvard University who formalized this a lot. Modeling and simulation, this is what we'll talk about a lot in this lecture. Optimization, we'll touch upon this a little bit as well. Life cycle analysis, stakeholders analysis. These are all methodologies that have been developed and are used to study some of these classes of systems that I just described. In this module, we won't go in detail to all of these, but I just want to give you an overview of what are the types of methods that are used when we consider systems analysis. Okay, so let's talk a little bit quickly about modeling and simulation. So I took this chart from Blanchard. He wrote a seminal book on systems engineering, which we still use. This was one of his early editions. There are many other editions after this 1981 as well, but I like the classic one better. And this is a nice sort of stepwise framework that he proposed in what's involved when we're studying a system. Okay, so it's really common sense, but he's laid it out nicely. So I have this here for your reference, and you feel free to get into it in more detail. Excuse me, but essentially the idea is that you first define the problem and the analysis goals. These two things are very important because you may be talking about very different problems, so it's very important to define what it is that you're studying and what do you want to get out of this analysis. Depending on that, it will inform your choice of approach, the evaluation criteria that you will use, and many other things. So these two steps are actually very important. They're common sense, but many people don't do these things, right? And then you sort of go through this, you define, your measures of evaluation, you define your variables, what are the data that you need, you select a suitable technique, you collect the necessary data, and then you run your models, perform sensitivity analysis, and then conduct a number of post-analysis studies. Okay, so we'll go through some of these steps in a simple example that I'll show you of a real systems analysis study that we did, in which we tried to quantify the water intensity of the urban water cycle. So this is an issue that is of great interest in many countries, Australia, the Middle East, USA. A lot of municipalities and many cities have been concerned about the use of energy in providing water to the urban users. If you actually look at the cost for providing water in a municipality, 80% of their costs are the power costs. Basically, 80% of the cost that a utility incurs or municipality incurs in providing water for the residents. This is, again, data based on the US case. I don't know what it is for Pakistan, but it's actually a significant number. So energy costs are actually a big fraction of the cost for providing water in many of these places. So people have been very interested in trying to understand, well, where is this energy consumption happening? So a number of studies have been done. And you have to do it really on a regional basis because there are many differences that of course arise depending on the area that you're looking at. So here's a simple problem that we set up. So our problem was that we wanted to quantify the water energy coupling at the urban scale. And the approach was that we essentially did building level modeling of water use and the related energy consumption and how it varied over time. Okay. The main uncertainty drivers that one can look at over time, which we didn't do in the study, is how would climate change and population growth impact this, and the main parameters that affect this is urban form. How do you design a city? How tall are the buildings? What's the temperature profile and so forth? All of these factors impact the results that you'll get. So here's our system boundary. So what it is that we're talking about here in this problem, we're looking at building scale, and we basically simplified a building in this way. So we're going to consider, how high the building is, how many floors it has, and we're going to give different options for supplying water at the building scale. The building may use rainwater tanks. In many countries, they mandate this. In Australia, actually, every new house that's built in Queensland, you're mandated to put in a rainwater tank. Okay. The building may draw water from municipal supply, and there may be limited recycling of grey water that is generated in the building. So grey water is basically the water that is coming off kitchen sinks and showers and so forth. So it doesn't contain solid waste, and it can be reasonably recycled. And if it's a large building, some buildings will put grey water recycling in there. Okay, so So you assume basically, so you basically describe the system that you will be studying, and you'll do this at the city level. So here it is. Here are some governing equations. I won't go through in detail. Just want to show you that these are some physics-based and a little bit empirical-based equations that we use to quantify the energy associated with water use for different types. We put these equations in a computer model, and essentially create a whole analytical framework in which we can vary different parameters. We can vary parameters of the buildings. We can vary the demand types and so forth. And then we will get essentially city-level water and energy computation and some results and evaluation in the end. Okay.
This entire is basically just energy balance.
No, there's not energy balance. This is showing how we implemented this this framework in a computational model in MATLAB. This is not energy balance. This is basically, these equations are computing the energy associated with different stages of the water use. And this is essentially showing you a schematic of the model that was developed. Okay? Okay. Here are some sample results, right? So this is a result of the simulation, right? We built the model, we put the equations in, we defined the parameters, and now when we're putting in different inputs, certain demand for water and a certain profile for the city, we can see how some of the things may work. So we can see the municipal supply, maybe the volume of rainwater utilized, and the energy associated with the water. Okay, this is for a particular building on plot A01. Just a simulation to show you what we mean by simulation results. Then we basically applied it for a case study in Masdar City. So yesterday you were hearing from Dr. Iftikhar from Masdar Institute. So Masdar City is basically, it's not really a city, it's basically sort of a new urban development, if you will, at the outskirts of Abu Dhabi. It's 6 square kilometers, 50,000 residents. It has a university, a technology park, some offices, and some residential areas. So it's really sort of a new urban development from scratch. And the big thing was that they wanted to design this to be the first net zero carbon city. So sustainability, environmental sustainability was a big part of the city's design. So we thought it would be a good idea to perhaps look at this city in detail and see what does this urban water cycle look like in terms of energy consumption. So here's the master plan. You can see, the different types of zoning that has been done, and we had data, plot level data, building level data for this master plan that we used to then estimate what it means for, or what it would be for the energy consumption related to water use. Okay, so here are some coefficients that we used to estimate the water demand. These coefficients are sort of the industry standard, May's standard handbook for water supply, provides this. And then we use some coefficients based on the Masdar baseline plan, which provides what are the estimates they were making as they were designing the city. This city was designed by Foster and Norman, which is basically a very prestigious architectural firm. They're based in the UK. They've designed a number of urban developments and so forth. So this was an interesting sort of case to look at. Here's a sort of example of the model run in which we are estimating different demands for the water under different scenarios. So we estimated residential, commercial, industrial usages at 3 levels, low, average, and high, and then we enumerated all the different combinations. We checked our results with some of the results that had been provided for the city in which they were estimating the water demand based on the baseline plan. We checked how well does our model work. You can see the analysis. This is an important part of modeling. When you come up with the model, it's very important to benchmark and validate how good are your results as compared to perhaps some known results that are already produced through some other means. Okay, so it's important to do that. And here are some sample results, right? So for the various levels of annual water demand, you can now estimate the energy associated with the water cycle. You can see the level here. I won't go into detail because the whole purpose is not to go into the details of what it means, but just to show you the process of conducting a systems analysis for the question at hand, okay? One key result that we found was that essentially the energy associated with the indoor water use was almost the same as the energy for desalination. So in Masdar City, most of their water, in fact, all of their water is sourced from desalination plants. Yesterday, you heard Dr. Iftikhar talking about how desalination is very energy intensive because you're essentially, separating salt water, separating salt from seawater, and that's an energy intensive process. What we found, for Masdar City, we used a value of about 4 kilowatt hours per cubic meters, which is sort of, what they have right now. Excuse me. The best you can do right now with reverse osmosis is 2 to 3. We're using value 4 here. But urban indoor end use is around 3 kilowatt hours per cubic meters, which is pretty energy intensive. So what does this mean? Okay, so we went through, we did all the modeling, we computed all of the results. So what? So this is actually very important. So if you were if you were the CEO of a municipality, or if you were the city mayor, or you were in some government agency, thinking about sustainability, thinking about carbon emissions, thinking about trying to reduce energy, this is not telling you the levers you can press. It's not about just moving your water source away from desalination to maybe something else. It's also showing you that the end use segment, this is people using water in their buildings. They're also a very important part of this equation. Right? So you can only go so far in addressing your energy intensity issue by just looking at water supplies that are less demanding on energy. You also have to address the issue of the urban indoor use. Okay, and where does a lot of this energy come from? Believe it or not, but it's actually not surprising, it's actually water we make. Yesterday you heard Dr. Sahar talk about specific heat capacity water. Water is actually has one of the highest heat capacity. It takes a ton of energy, actually, 4,000 plus kilojoules to raise the temperature of water just by 1 degree. Okay, so it is because of this property of water that you actually have to expend a lot of energy to heat it. And the UK and so forth, people have done calculations with the US as well. Of the total energy bill that you get in your house, 25% or more is related to water heating. So think of all the energy that goes in the boilers to heat the water and to get warm. So in cold countries, actually, it's a big issue. But even in warm climates where you're using hot water, there's an energy cost associated with it. And because of the high heat capacity water, it's basically the water chemistry that's driving. So these things are important, and they will only come out when you actually do the analysis. This is something maybe most people may not have thought of just by thinking through this issue in your head. Okay. So here's this example. So some key results that you will find that give you additional insights and how do you sort of deal with this issue is essentially that water efficiency and end use has largest multiplier effects. So if actually reduce the amount of water that's used in homes, it not only reduces water, but it also reduces the energy use, right? And a lot of people have talked about that as well. This is showing this quantitatively here, okay? And you may know things qualitatively, but until you do the analysis, you won't really know what's the level of energy involved and how much can you get if you were to introduce certain policies or certain behavioral changes and so forth. So I hope this illustrates the kinds of analysis and the types of studies one can do. This is really just for illustrative purposes, but I hope it gives you the main point. Now moving back to Pakistan, this example was drawn from UAE, and here we are at this water seminar. There are critical challenges, right, for energy, water, and food security. And some of these challenges are not just about understanding, how all of these systems are interconnected or what some of these large-scale systems, how they may be performing, but how do we get them to perform better? How do we make the best use of these resources available? Okay, and systems analysis techniques allow us a set of tools to answer some of these questions. So in the case of Pakistan, here's a population pyramid, right? And we were talking about this yesterday. We're a very young country. The majority of our population is, under 20 years or so. And what does that mean? Well, that means that we have growing need for basic resources, right? For energy, for food, for water. We heard a lot about, the water stress, so-called water stress in Pakistan because of population growth. But similarly, I don't think I have to explain what this means. We've all experienced, load shedding and power outages and cuts, shortages in power, shortages in food supply. So it's hardly an encouraging curve, right? You can see all these oscillations and instabilities here. So certainly there are a lot of urgent needs in which we want to make the best use of the available resources, right, to meet these growing demands. And essentially we have a set of fixed constraints of our resources of land and water, right? We're not getting any more new land, and we're not getting any new additional water supply unless we start large-scale desalination. So here you have these constraints that are resources. What's the best use that we can make of them so that we can meet some of our growing needs, right? This is a very relevant question to ask. And optimization methods are basically a set of techniques that allow us to answer just these types of questions, okay? How many of you have studied optimization before or use it in your professional work? I just want to get a sense. So fair number. arbitrary number. Okay, good. So then you'll help me through as we go through some of these problems, and we'll go through this together. Great. So when I talk about optimization, essentially we're trying to either maximize or minimize some quantity so that we can get our desired objective to the best possible level, right? So a typical maximization problem is maximizing some kind of output or profit subject to a budget or other constraints, right? So what's the maximum I can get out of this farm, right? What set of crops or what type of techniques can I employ so that I get highest agricultural profit out of my farm? Or what can I produce from this factory so that I can maximize my profits? But I can't do that in a limitless way, right? There are very real budgetary constraints, technical constraints, and so forth that I have to operate under. So that's the set of constraints that we have to account for, right? So the question is, how much can I obtain from a farm or a factory or a power plant or a coal mine with the amount of money and resources I have, given that we need to operate within the technical, economic, legal, and political realities, right? There are a lot of legal frameworks that come in and act as constraints and so forth. A minimization problem may look something like this, right? That the question is, how cheaply can we produce our output while meeting all the technical requirements and other standards, right? So for example, when Magdar, wants to lay out its plans for expanding its capacity, it usually does a least cost generation plan, right? So it looks at all the different options, right? So, and then it basically picks the ones that are the cheapest. How can you produce electricity at the cheapest rate? Although in reality, that doesn't always happen. Yes. Yes, absolutely. So the key question is, how are you formulating your objective function? So that's the holy grail, right? How do you get your objective function right? And it gets very hard because if you use some of the methods that are used, in financial analysis. So let's say you're doing an NPV calculation. What you end up doing is you end up discounting the future very heavily in traditional analysis, and that is why a lot of short-term decisions are made, because this whole issue of, the present value of money problem, right? That money today is more valuable than money tomorrow, and all these NPV calculations skew your decisions towards short-term goals. But now, there's more and more recognition that, we have to stop this, and people are trying to come up with all kinds of formulations that how do you really weigh your future legitimately and at the appropriate level, just the way you're weighing the present. That's right. So this is a loaded question. You can have a whole course on this. Okay, so this is, so essentially it's maximization, minimization problems that we're typically dealing with when we use optimization. And in this module, in this lecture, of course, in 90 minutes, you're only going to get an overview of what this means and the types of problems you can use. We'll focus only on linear optimization and, again, only touch on it. I've put up a number of references at the back here. Welcome to, look this up. If you're interested in this topic, you'll find many, many good resources talking about linear optimization. But there are many other ways and many other techniques that are within this umbrella of optimization, non-linear optimization, many different types of methods and so forth. We won't be covering that here. Linear optimization really started around the 1940s, the Second World War, really led to... Yeah. So what you do is basically you formulate your objective function in which you subtract out the cost, right? It's just a way of formulating it and how you choose to do it. So we'll go through an example to get a sense of it, but it's semantics here. It's really how you want to set up the problem and what you're trying to do here. So linear optimization, has its roots in mathematics for a long period of time, but it really became sort of an active area of study and use around the Second World War. In 1940s and 50s, they developed a lot of good algorithms and theories. There were a lot of proofs that came about in the 1950s that show that how do you, prove that an optimal solution that you found is really optimal and so forth. And there's a lot of rigorous mathematics that goes that's behind this field. We won't touch on that, but it really was so powerful that it led to very rapid and wide use of this technique in real-world problems and in real applications. So when you look at Amazon, they're running a big linear optimization program and many other optimization programs in which they're trying to minimize their service delivery time, maximize costs, and maximize customer satisfaction and so forth. Really, that's what Amazon does. And many other such companies that are based on logistics, that are based on supply chains and so forth. So optimization is a big deal. So the different types of areas where this is now widely employed and used ranges all the way from engineering design, where you basically try to design systems for some maximum level of performance. Planning, as I just told you about, usually electricity capacity expansion uses some kind of optimization technique, management and operations. So this is supply chains, logistics, and so forth. So optimizing, operations of airports, of supply chains, of many other things. All of these are using optimization methods at large scale. And then very importantly, banks. So a lot of investment portfolios are basically running, optimization programs in which they're trying to optimize how do I invest my money, where do we invest our clients' money so that we can maximize the profit over a period of time. These are the different opportunities for investment, these are the different rates of return for profit. How do I allocate a given set of cash or a given set of assets so that I maximize my profit? This is something very real, very applied, and very much in use today in a lot of key industries that we encounter. Just a little thing here that linear optimization is sometimes called linear programming. Don't be confused by the two, they're the same thing. It's called linear programming for the historical reasons, because people would write computer programs and run the optimization. Now there are a lot of software tools available, so we don't have to do that. They're still referred to linear programming in many cases, but essentially they're talking about linear optimization. Okay, so how do we go about formulating a linear optimization problem? There are really two parts of a linear optimization problem. One is the objective function, and the other set of constraints. Those two things comprise formulation of the linear optimization problem. Okay. So what is the objective function? Essentially, an equation that defines the quantity that you want to optimize. Okay. For linear programming, it is always a one-dimensional scalar quantity, right? So it's basically one thing, the profits, right? Or maybe cost, or something else. You're not doing two or three things, just one thing. That's what we mean by a scalar. Okay, so one objective. And the objective function involves a number of variables, and these are known as the decision variables. These are the variables. These are the things that you want to make decisions of. Okay, so when you're a banker and you want to know how much money do I invest in the stock market, maybe in real estate equity and so forth, then your decision variable is the amount of money in stocks, the amount of money in real estate, the amount of money in something else. Okay, so those are your decision variables, the amount of money invested in different assets. Similarly, if you are an engineer, your X's may relate to specifications of different design components and so forth. Okay, so X's are the decision variables, and they show up in the objective function as a linear equation. Okay, so Y here is the objective you're trying to maximize, and it's basically a sum of C's are the constants. These are constants, and X's are the decision variables. So everybody understand what this equation means? Yeah? Right? So essentially, right? So Y is sum of C1 x1 plus C2 x2 and so on, depending on how many you want to have. Yeah? And these X's, these are the decision variables that we have in our problem. And these C's are basically constant terms. These are just constants, okay? So that's a typical formulation. The constraints are also linear in a linear optimization problem, okay? So they're also essentially of this form here, where you have an equation, linear equations of X's of your decision variables, and there are some upper or lower bounds on your equation variables, okay? So similarly, this equation reads exactly like this, where B is a constant. So let's follow through an example and see how do we, operationalize some of these things that we just talked about. So I just picked a toy problem to get everybody on the same page here. So let's say you're the CEO of a company. You just graduated from Lund with a degree in economics, and you were put in charge for Soltech, right? And it's a company that makes 4 different types of products for the solar power industry. Okay, so maybe one type maybe is used in farms or groundwater pumping, maybe another type of product is used for homes, when the electricity goes off, you can turn that up as a backup, or maybe it's always there, and so forth. And maybe you have 2 other different types of solar power products. Okay, so you have 4 different types of products that you're making. You're the CEO, and the company's president comes down and says, I want you to pick basically a set of volume for these 4 different types of products so that you maximize the profits at the end of the year. This is your job, okay? So how do you do that? Well, you set up the problem by first analyzing, gathering all the data, and this is what the data looks like, okay? So these are 1, 2, 3, 4 different types of products, and each product requires these following things. For each product, you need to use 2 types of different machines, okay? Machine 1 and machine 2. And you need 2 types of labor. So skilled labor, maybe these are the engineers, or maybe these are the technicians that have an associate's degree or so forth. They're a little more costly. And then you have unskilled labor also that are doing some of the other things. Okay, so they come at different cost rates, right? The unit price that you can charge to sell one of these products is listed as follows. So some things are more expensive, others less so. Okay, how do you sort of figure out what's the best combination of production so that I maximize my profits? If I only go for the expensive ones, actually, I also am using more labor that is also more expensive, right? So it's not just simply saying that, oh, I'll just produce the one that's the most expensive, that sells at the highest rate. It's not as simple as that. And if you actually analyze this closely, you'll find that just by looking at this data, in your mind, you're not going to be able to determine what's the optimal solution. You really have to go through it and do the math here. Okay, so let's do the math. This was the data. We have a bunch of constraints as well. Okay, so let's. Here is one that each month you have only 700 hours available on machine 1. Okay, and that's very normal. Maybe you might be leasing the machine, and there may be another bunch of businesses using that machine. So your time on that machine is over 700 hours, or there may be other constraints. Maybe the corporation has other companies that are using that machine as well. You have basically 700 hours available on machine 1, 500 hours on machine 2. Okay, you can purchase up to 600 hours of skilled labor. Okay, $8 an hour, and you can purchase up to 650 hours of unskilled labor, $6 an hour. Okay, so maybe the economy is good, maybe the bad, the company decides to pay its employees in dollars. Okay, so here we are at this rate. I was too lazy to convert it into rupees, but you get the idea. Okay, so how much of each product should the company produce each month, and how much labor it should purchase to maximize profit? Okay, so what are the decision variables? Can somebody help me out here? So if you want to pose an optimization problem, and this is a question I'm asked, or I'm trying to figure out, what are my decision variables?
Would be the labor hours available and the machine hours.
Okay, so the labor hours of, unskilled and skilled, right? So this is unskilled, and this is skilled. What else?
And machine hours.
Machine 1 and 2. Well, so look at the question more clearly. How much of each product should the company produce? So ultimately what we're interested in is how much of product 1 do we produce? How much of product 2 do we produce? Sorry, my clock keeps waiting. How much of product 3 and how much of product 4? Ultimately that's what we're asking at the high level, right? How much of each product should the company produce? So what we're asking is that how much should of 1, 2, and 3 should we be producing? How many units of products 1, 2, and 3 should we be producing? And how much labor should we be purchasing? Number of hours of unskilled and number of hours of skilled labor. So this is just translating this English into representation in variable form. That's all I'm doing at this moment. But we'll get into the constraints of what you're saying. I know what you're doing is essentially referring to some of the constraints that you mentioned. So let's walk through this. Okay. So some of the variables here, right? Right. So essentially, what it's asking is that what are X1 through X4, the quantity of each product of each type, right? And the hours for skilled and unskilled labor, right? Okay. So this was the data that we had, right? And the question that we had. Let's go into the objective function. What is it that they want us to do? what are the maximize the profits, right? So that's the objective function. We want to maximize the profit, and the question here specifies it clearly that what they mean by profit is revenue from sales minus the labor cost. So what is the revenue from sales if we know that we produce, let's say whatever we produce we also sell, we're making an assumption here. If we're producing this level of these 4 products, what is the revenue that we get? Can somebody help me out here? Yes. So what is the price of product 1? Exactly, right? So that's 300 x1, 300 times x1, right? Plus, exactly. So you guys get the idea, right? So we multiply the price with the product volume, and we do that, right? So I will cut to the chase here, and this is our objective function. So the price multiplied with the volume of product produced, and we subtract out the costs. These are the labor costs, right? So simple. This is the objective function that we want to maximize. This is our profit, right? The price, the revenue that we get from selling minus the cost. So it's simple, right? Okay. Now look at the constraints. How do we convert the constraints in English from English into math? Okay. So again, maybe you guys are thinking I'm back in high school days, but let's follow through. All right. So. The first constraint was that each month 700 hours are available on machine 1 and 500 on machine 2. So what does that mean? Basically what that means is that machine 1, for machine 1, product 1 requires 11 hours, product 4 requires 5 hours, and so forth. What this means is that basically whatever quantity of products we produce, this whole amount of time, because quantity of x1 times 11 hours that it took to produce it, you sum it all across all the products, should be less than or equal to 700. That's basically what that constraint means in math, right?
If you're saying that this thing is constrained on machine hours because they have fixed quantity.
Yes.
And labor hour is fixed as well by department.
We'll do that. You're always ahead of me. So we'll do that. Good thinking. We'll come to that. That's right. Okay. So this is the constraint for machine 1. I like that. So please feel free to interrupt. This is the constraint for machine 2, where we said that we have 500 hours available for machine 2. So basically 500, right? Okay. So we're basically just going through systematically and converting all English into math here. And then the skill labors, right? This is a constraint that we have. That basically, whatever quantity of products we produce, for X1, it's going to take 8 hours per unit. You sum it all up all the way, and that should be less than or equal to the total number of hours that we purchase for the skilled labor. Okay. Similarly, for unskilled labor. And we also said that the maximum that we can purchase for these 2 types is basically 600 hours and 650 hours. So basically, this is the other set of constraints. Okay. Now, going through and coming up with these equations may seem actually simple, but in reality, this is often not that easy. Because what happens in reality is that you may miss some important constraint, and when you run the optimization, the solver will say that your problem is unbounded. Or it may give you some other kinds of errors. You don't go into that. But just going through this process is actually not a trivial process in its own right when you're doing a real-world problem. Getting the formulation for the objective function right and getting the formulation for the constraint right is actually a very important step, and it's not trivial. I've used a small toy problem to show what it is, but this itself requires some deep thinking and a good knowledge of the problem that you're trying to address. Okay, so one last constraint that I'll put on the problem, which is that all of our variables need to be positive, right? So we're not going to be producing -2 pumps, and we're not going to be getting -3 hours of skilled labor and so forth. And this is an important constraint for linear optimization. Linear optimization uses variables and needs variables that are positive, okay? It doesn't work on negative variables. There are other ways in which you can deal with negative variables, but standard formulation of a linear optimization problem, you need to have this constraint in there, okay? Okay, so far so good? All right, so now what do we do? So now we've come up with these equations, we've set up the problem. now we can go through and use some of the solvers that are widely available. I'll show you one that I typically use in my work, which is MATLAB. But some of the ones that do large-scale optimization, you know, with thousands of constraints and equations and so forth. So Cplex, this is a very powerful tool. GAMS, which I'll give you a very quick example of a good application that has been developed in GAMS. Even Excel has actually optimization tools in it. Excuse me. So here's, let me first show you. All right. So I brought up the optimization toolbox here in MATLAB. Wow, this doesn't look very nice here on the screen, does it? Maybe it looks fine here, but maybe that's fine. It's not a big deal. I just want to show you that in MATLAB, what it does is the linprog function, linear programming function. It basically minimizes a given function subject to, you know, a set of linear constraints. So the key thing to recognize is that it's minimizing the given objective function. What did we want to do in our objective function here in the problem? Exactly. So what we'll do is we'll enter the negative of that formulation, okay? Because the program here, the function here in MATLAB has been coded so that it only does minimizations. So if you have a problem in which you want to do the maximization, you simply just basically negate the formulation. You put negative sign. And then once you get the solution, you convert it back. As simple as that. But this is an important thing to recognize. Okay? All right, so let's do that. I set up the problem here. It's very simple. I won't go through the details, but you basically can set it up. You can describe the problem here. The lower bounds, the upper bounds. These are the set of equations that we just wrote over there. These are the constant coefficients and the bounds. And this is our objective function right here, the 360, 250, and so forth. And notice that I'm multiplying it with a negative 1 here. This is the key step, okay? So I run the program. All right. And it turns out the solution. So this is the solution here, F val. And notice that this is a negative quantity. Okay, let me put this out here, and it's basically showing me 15,433. So basically, this is negative. You convert it back into positive, and what it basically is showing is that the maximum profit I can get is $15,333, and this is what I was looking for, the x's, right? So this is the solution to the 6 decision variables I had. So for product x1, it's 16.66. So I need to make 16.66 units of product 1. Okay? And then so forth. So can I make 16.66 units of product 1? No, not really, right? So in reality, what you'll do is that you'll essentially convert this into an integer. If you really want to be choosy, you can do integer programming, which is a lot more computationally expensive. So what people do is, even when the decision variables are integers, because in reality, what the decision variables were integers, and in a normal linear program, you assume continuous values for your decision variable, right? So x is a continuous variable. In reality, it's really an integer. So a common turnaround, which is fine, which is widely used, is that you run it as a continuous variable, you run your problem as a continuous variable, but when you get a solution, you convert it into integers as needed, and that's an acceptable way of doing things. If you really want to be picky and you want to go into integer-based optimization, there are different methods that allow you to do that, but here we won't cover that, okay? So here, similarly, if I go through, these are my lives. So 583.4 hours of unskilled labor and 650 hours of skilled labor, right? So it hit the constraint actually. Okay. Now there are lots of other things that you can do with this solution.
The question about that, if we are changing sign for the objective function, then we have to change something in constraint also. We have to change the equality sign, unequality sign.
No. So it basically, takes care of all of that in the software, and it's actually, you don't have to change that, because if you think about it, you're just doing a reversal, right? Just a reflection of your function. So you don't have to worry about changing the signs of the inequalities. It's just the objective function that you can switch, and maximum and minimum will get taken care of. If you think about it, right? Yeah. Anything else? That is right. That is right. So product 3 is actually 0. Right. That's right. So I'm just showing you all the quirks that you will get when you actually run it in a software, but then you have to make sense of the solution. So here, it's a very tiny number. So, you know, the optimizer was working and it basically, it's effectively 0, but it just, it spit out this really tiny, you know, 1.9 e to the 10 to the negative 7 number here. But essentially meaning that no product 3, right? Okay, and then similarly, what you can see is that for number 6 is that it hit a constraint. So there's a whole step that you can do later on, which we won't get into here because again, in the interest of time. But essentially, it focuses on sensitivity analysis, in which what you basically do is that you say, okay, now I have my optimal solution. The maximum profit I can get is $50,300, and this is the number of products I need to make for each type, and so forth. But what if I were to relax a particular constraint? What if I don't want to bind myself to buy the 700 hours of machine 1? What if I could pay a little bit more and relax some of that constraint? How much should I pay for that? You may want to ask that question. You can answer those types of questions by starting to do the sensitivity analysis, in which you basically see what's the improvement in the objective function do I get if I were to change one of the constraints, right? And does that improvement then justify perhaps a little bit more expense? And if that, so let's say you were, I'm not going to do this here, but I'm just, you know, letting you think through that. Let's say we relax the constraint from 700 hours to 800 hours. You say, okay, fine, you buy another 100 hours. Can I get more profit that way? Well, in order to relax that constraint from 700 to 800, you have to pay a little bit more. So maybe we have to pay another $2,000. But the improvement in the objective function that will result, if I were to relax that constraint, is going to be $4,000. So my net result is still that I make another additional $2,000 profit. So it's worthwhile, perhaps, to spend a little bit more money and relax everything. You can start asking these types of questions. So you can quickly see that this type of approach is very powerful in management. And it's used very widely, as I said, in real-life applications in a number of industries. I had a question there.
Yeah, I wanted to ask that if the product 3 has been eliminated from the first iteration, then don't you think that the initial problem has changed because we have eliminated product 3 and now we're just left with 3 problems?
No, it wasn't the first iteration. It actually took 6 to get to this. But that is how, you know, it worked through the problem. So actually, let me show you a little bit more detail. If you want to get a nicer user interface, let me see if I have it up here. Yeah. So you can use, instead of, you know, writing it out here in a script form, you can use the optimization GUI which MATLAB provides. And most software that you use will have, you know, different types of this, in which you can basically specify your objective function and so forth. You can specify your equations and your bounds and so forth. And when I run it, right, you'll see that basically, okay, this solution is a lot more clear. And it did 5 iterations to get to this, actually. So what it does is essentially, just to give you a quick insight, since you guys seem to be curious and I like that, I had a little picture. First I thought I would draw it on the board, but so when you're essentially doing a linear optimization problem, what you're doing is essentially you're traversing the edges of a polyhedron in 2D space and multiple dimensions. It'll be a polytope or whatever it's called. But essentially the idea is that, think about this, if you have 2 variables in a linear relationship, x1 and x2, right, that you want to maximize, it essentially means that here's your space x1, here's your vector x, dimension x1, here's the dimension x2, so all of this space, you know, x1, x2, you want to find 2 points where you have the maximum sum. You can't find that maximum until you constrain that space. Otherwise, if you don't have any constraint, there is no solution because you just go to infinity, basically, right? So in order to have a meaningful solution, you have a set of constraints, okay, which are these. So some of these x1 and x2 should be less than or equal to 3, okay, which is this constraint here, this line. Here's my pointer. Okay, this is that constraint. X1 should be less than or equal to 2. So here we draw this line here, and x1 should be somewhere on to the left of this line. Similarly for x2 we have, and they both need to be positive. So what this gray shaded area represents is actually the feasible region. This is the region in which you want to pick x1 and x2 such that you get the maximum sum. Okay? And if you look at the shape of this region, what you quickly see is that the maximum will lie somewhere around the edges of this shape. And what the algorithm is essentially doing is that it's traversing along all of these vertices of this shape. And then it picks the one where it finds that it can no longer improve the difference. That's how the algorithm is actually working inside. And there are different ways in how do you quickly do that. That's another whole area of mathematics, and how do you quickly traverse that space as well.
What if we have eliminated x3 from the problem and we are getting the same solution?
Yeah, that's a good point. That if we're not producing x3, would it change? It would change the structure of the problem, yes. And you'll have to probably, you know, exactly. And it's about, you know, not just x3, it's also the constraints that come into it. So if you were to change, let's say, some of the C's and the A's associated with x3, you may get different solutions. So for this particular instantiation of the problem, x3 was 0. But in another one, it may not be. You know what I'm saying? So in another one, if the C's and B's were different, it may not be 0. So I wouldn't quickly jump to the conclusion that let's just eliminate it from the problem altogether. Yeah, that's the optimal solution. Yeah, if that's what you're asking, you're right. Yeah. It's part of your decision space, and that's an important thing to consider, right? Because here you have a decision space, right, along multiple dimensions, right? And as a manager, you have a lot of these valid choices to make, and as Dr. Berger explained, that your solution showed that the best choice to make for the optimal case is not to produce any x3 at all. But it is still part of your decision space because this is one of the product lines in your company. So you want to consider it in your problem, right? Yeah.
So does this discussion end with suggesting that we should eliminate product P and start another optimization model with 3 products as additional products?
So it depends on what you want to do. It depends on what you want to do. So if you want to sort of, you know, consider this world where you don't produce any x3, you could run that, certainly, and you can run with all of these possibilities. But I will come back to, you know, what we originally said, that if, let's say, you have a sunk cost in your company, you have the ability and it's on your portfolio that you're producing it, there may be reasons why you may not want to take it out.
But it depends at the prevailing situation.
Yeah.
At this moment, it is like that.
Exactly.
After some time, it could change because your conditions are changing.
Exactly.
And then you can decide that you can go for x3 also if that is the optimized.
Exactly. Yeah. Okay. So is that good? Okay. So I'm going to just summarize what we just talked about. Okay. So the typical steps in a linear optimization process is that you formulate the problem mathematically, right? You convert the English or the Urdu into math, right? Then you basically represent the various parameters that the decision maker or designer wants to determine, right? These are your unknowns. You express the objective function mathematically. You express the constraints mathematically. And then once you have a well-posed, nicely formulated problem, you can then solve and find the optimal solution using a number of these packages that are now widely available. Okay? All right, so enough of this FOIA problem. Let's take a look at a real-world example. Right, so this is a model that was developed for the Indus Basin using basically concepts and implementing linear optimization at a decent level. I personally, you know, the disclaimer is that I personally have not used this model, but I've seen it and I've seen papers produce from it, and I'm hoping maybe when you guys finish this course over the week and you become modeling experts, so hopefully we'll get a few people working with Professor Abubakar here on IBMR, inshallah. So, so this was developed in the 1980s, and if you talk to any sort of hydrologist that according to Professor James Westcott, this was the most detailed and impressive model built in its time, and it still is considered one of the good models. So this is not just something about Pakistan. Even in the field, it was actually considered one of the most detailed models ever built for a river basin, in which basically they simplified the Indus Basin into 12 agro-economical zones. Okay. And the problem that they were trying to solve was that how do we best allocate water among these different zones and areas and cropping patterns so we maximize agricultural profits. So the problem was basically looking at basin level optimization, and it was essentially trying to look at what's the best cropping patterns and what are the best ways of allocating water resources so you can maximize profit. So this is not doing farm level optimization, and this is not doing prevention scale, this is doing basin scale. And this is an important thing to consider, because imagine if you start introducing constraints at different levels, at the provincial level, and perhaps other scales and so on, the solution may change. And this is, one of the things that you can do very well with these types of models. Is once you have these models, you can start looking at different scenarios. And what's the impact of different policies? What is the impact of different types of regulations on your optimal solution? Okay. So, but just to come back, this one was looking at basin scale optimization. It is still being used. The original one was developed funding from the World Bank in the 1980s. They did a bit of work with it, and in recent years, it has been revised. So the current model is called Indus Basin Model Revised, IBMR. It's widely available. If you actually just Google, Indus Basin Model, you'll find the model, the original one that was built. It was coded in GAMS, which is basically a high-level algebraic modeling program in which you can specify different equations and so forth, and run linear optimization by plugging it with some kind of optimizer. So you can couple it with Cplex, you can couple it with some other packages and so forth. A more recent study was done in 2013 by another group of the World Bank, Winston Yu and Yi Chen Yang and so forth. Professor Westcott, you saw his video yesterday, and he's very much part of the center here. He was also part of the study, and they issued a very detailed report in 2013 that's also available. You're welcome to take a look at it. It's very interesting. Just to give you an overview of what the model does, as I just mentioned, it divides the basin into 12 zones, and essentially has a bunch of equations that take care of the water balance, that essentially include crop production, canal irrigations, and so forth, and then they optimize a linear objective function, right? So this is a real formulation of an actual case in which you have a bunch of summations. I won't go into what all of these different things are. We haven't talked about slash variables and many other things, but just to give you a view that these things are very much used. These types of formulations are very important and valid and used in real-world applications. Okay. There have been several updates that have been made over the years, as I just said. In IBMR, what they've included is basically hydropower profits. So in the original model, they were only looking at agricultural production. In the newer versions, they've tried to include hydropower profits. They've also extended the IBMR from a single year to multi-year, so you can capture the effects of storages and many other things from year to year and so forth. As well as they've updated the data, so a lot of constants that were there that have been updated to reflect more current data and so forth. So a lot of effort was done in recent years too. So that is IBMR, and the objective function has changed a little bit as well. So you can go through the report, it's all there, it's well documented, and for those of you who are interested, you can see what has been done. Here's just a snapshot of some sample results. Right, so looking at different water scenarios and looking at different policy options here. So you can see, they did a number of different cases in which they looked at IRSA rules. So basically how the water is allocated across different provinces, and you put those constraints as specified by IRSA. So, that many million acre feet for Punjab, that many million acre feet for Sindh and so forth, and if you specify those constraints, what are the maximum, minimum profits that you can get in the agricultural sector? And in the revised version, what they also did was they included the water needs for domestic users and industry users, which was not the case in the original model as well. So in IDMR, they included domestic and industry sectors as well as hydropower, right? And you can see it under a different variety of situations. This is basically domestic and industry with groundwater. They looked at situations where they capped groundwater pumping at certain levels, so they put a constraint that total groundwater pumping cannot be above 50 million acre feet in 1 year, because usually the assumption is that the groundwater that we have is about 50 million acre feet at the basin level. So they just put a cap that let's not over pump, so let's not mine our aquifer. So you can now play with a number of scenario situations and look at these different options. So this is the case in which it's the optimal allocation policy, in which they basically say that, okay, what if we relax some of those rules? What results would we get? And this one is and what they say in this optimal policy is that they say that the provinces can trade water. So basically, Punjab will get its share that it has allocated, and Sindh gets its share that it has allocated, but let the provinces now do whatever they want with their share. So if Sindh finds it better that instead of doing low-value agriculture, we may sell it to Balochistan or something else, the provinces can trade. So they still own their water rights, but they have the right to trade, and many other things. And this one is basically just looking at basin level optimization. So no constraints, no nothing, and you basically just send water to the best user for optimal productivity and so forth. So it's a very interesting study. You guys are welcome to take a look at it in detail for those of you who are interested. This about wraps up my time. I think we're 10 minutes ahead, so that's good. We'll have time for discussion here. I'll just give a quick review of some of the things that we considered, right? So linear optimization, right? It's problem of optimizing an objective function. Expressed as a linear function of discrete variables and constraints, right? So that's key. And a feasible solution, actually, I didn't talk about this. So the feasible solution is any assignment of values in which all the constraints are met, but it may not be an optimal solution, right? So for instance, remember the little picture that we drew over here, right? Let's say in the 2D case, right? You had this, that. Right, this was a feasible solution, right? So any point that you pick in this region is a feasible solution because it fulfills all the constraints, but it's not the optimal solution. It's not maximizing the objective that we have set, right? So that's different between a feasible and an optimal solution. In many complex problems, many of the types of problems that I work with, you may be happy just finding a feasible solution. Basically a solution that satisfies all the constraints. It's called satisficing. You can't even dream of optimization because the problem is so complex, but just satisficing is considered enough. So that's all about finding feasible solution.
Optimum solution is feasible region.
Yes, so the optimal, exactly. That's by definition. The optimal solution is one that is fulfilling the constraints, absolutely. Okay, and the goal of linear optimization is basically, find an optimal solution that fulfills the constraints, and it's a very powerful tool for planning and resource use efficiency. So IDMR, as I just mentioned, is a real-world example for our region where these types of models have been developed. I think the challenge going forward is that a lot of these tools exist. There's another model called PARC IEM, which was developed by the Energy Wing, the Planning Commission in Islamabad, which basically does planning for energy systems. These models exist and they've been developed, and a lot of good work has gone into them, but they're not used. The potential is not fully harnessed. They're not being used as they could be to inform some, to inform real decision making, to inform real policy. And what I'm highlighting here is that, when you guys graduate in Chalo, or many of the practitioners sitting here, I hope there's opportunity in the future that as more and more people recognize the utility and the importance of these things, they're included in decision making, and real world decision making. All right, so with that, I will close this session and I'll be happy to take questions. So I know we have the break after this, so people don't want to lose out on the break. Okay.
So,
It's very, it's very static in some ways, and the time resolution is 1 year, right? So basically, you look at the yearly crop pattern, so you do seasonal, but essentially, and the monthly year motivation is essentially just year to year. So they don't have time to play with at all. And this is, really long-term economic planning also. So you have to also recognize, what the model is trying to do. It wasn't really meant for scheduling, right? So it's not doing 10-daily scheduling. It's really doing sort of basin level, provincial level, sort of analysis that if this is cold water available, can it be used effectively? It's not really doing, canal scheduling. So the time resolution. Well, there's no conclusion. Basically, there's a whole bunch of scenarios that they comment on. What they basically concluded was that if you did, the provincial trading, you would be better off. One of the key findings that they had was that, okay, maybe if you allow for trading, you can actually improve your profits a little bit. But how do you implement that? That's okay. Yeah.
What this demonstrates is that you can set up legal framework and for certain problems. Okay, so we are very fortunate that
how does one validate the
Absolutely, absolutely. So we talked a little bit about benchmarking and so forth. That is a very important point of modeling, and that's one of the reasons why models are not trusted in many ways. Because how do you know that the answer that you're getting is actually true? It's an open question, and it depends on the level of rigor and trust you can build with the results. The model is doing it, and the decision maker is using it. For IBMR, they used best available data. How do you validate the optimal solutions? I don't know what exactly how do you prove that this would be in reality? Because the key question is, did you capture all the essential features of the system well? Because the solution that you're getting is the optimal solution to the mathematical set of equations that you posed. Do those mathematical equations represent reality? Is a very important question, and that's the art and science of modeling that I was mentioning earlier on. That it's not just about converting blindly equations into a solution. It's
the problem is also that you have memorized everything, but in reality things are not so linear, and then we optimize that. And in IBMR they did also so. If you are considering many things in basic processes which are going behind that, and then we are considering things. They are all linearized, but actually it's not.
But that issue of linear nonlinearity, there are lots of now tools and methods that deal with nonlinear optimization. IBMR is very much, of course, implemented in a linear way, and linear problems are still widely used because they guarantee optimality, right? Because of the feature of the complex space, where that once you find the optimum, that is the global optimum. But aside that, you're right. There are a lot of linear issues, and for nonlinear optimization, you may end up using methods that won't guarantee an optimal solution. And that certainly is an issue and a challenge.
There would be the development of a hierarchical model so that you could get to a smaller and smaller unit, and you get to some unit where you actually can measure the experimental parameters.
That's a good point. I'm not aware of any such effort that has been made.
So currently, NESMARC is doing this, so taking the IBMR model at high level and then doing it for now inter-provincial allocation. They are now doing it and coupling it with the actual methodology. So there is an effort.
But are they doing any experimentation to validate?
So that is the hope that ultimately they will be able to validate.
Take a district, look at all the crops, and then actually do some experiments that are more hard to do.
That's the agriculture. So that again, the agriculture part.
Agriculture is like 30 times the size of anything else, so everything else becomes very rare.
Because what IBMR does, from my understanding, is that it gives you the optimal cropping patterns, right? And that's hard to do experimentally. How do you tell farmers this is what you need? But you can do it at a small scale and at least see. Well, that's what you're talking about. Let's just do it at a small scale and see.